Hello dear students. In this session we are going to start the module unit 2 of the module 1, which is the network modeling. So that first session is network models. A network is simply a collection of objects connected to each other. Examples include social networks, communication networks, transportation systems and the internet. So the goal of network modeling is to understand how these connections form, how networks grow, and why they exhibit certain patterns. So why should I use network models? So imagine Facebook. Every friendship looks like an individual decision between two people. But when millions of people create friendships, a huge network emerges. So what do friendships form? What processes create these connections? How do millions of individual friendships become large complex structure? So that we are having the example of Facebook. With networks this large, analyzing every connection directly is almost impossible. Therefore, we need mathematical models that represent and explain these structures. So what do we do? Instead of studying real networks directly, we create models that generate graphs similar to real world networks. If our model accurately imitates reality, then we can analyze simulated networks instead of expensive real data, and we can understand why networks behave the way they do. We can perform experiments when real networks data is unavailable. The fractal images represents a complex pattern can emerge from a very simple rule. Similarly, social networks may look extremely complicated, but they might be generated by a few simple underlying principles. So that next we will see the properties of real world network. There are three very important properties: power law distribution, high clustering coefficient, small average path length. These characteristics appear repeatedly in social networks, web networks, citation networks and communication networks. So the next topic we will see the degree distribution. So the degree of a node means the number of connections it has. For example, if a Facebook user has 50 friends, the degree is 50. And another user has 500 friends, the degree is 500. So degree distribution tells us how many nodes have degree 1, 2, 3, 10 and 100 so on. So understanding this distribution helps us see how connectivity is spread throughout the network. Then distributions. So power law distributions appear in many real world situations. So that first one is wealth distribution. Most people have moderate wealth. Only a few people are extremely rich. City population. Most cities have average population. Only a few cities become huge metropolitan areas. Then social media. Most content gets modest attention. A small number of posts become viral. This phenomenon is closely connected to the Pareto principle, which is 80-20 rule. 80% of outcomes often come from 20% of causes. So that Herbert Simon studied these skewed distributions and showed that they occur naturally in many systems. So the next one is site popularity. Many websites receive fewer than 1,000 visits per month. A few sites receive millions of visits daily. And then user activity. Most users participate only a few online platforms, but some users are active across hundreds of sites. And then product price. Most products are moderately priced. Very expensive products are relatively rare. And then friendships. Most people have small number of friends. A handful of people have thousands or even millions of followers. So these friendship example directly leads us to degree distribution in social network. So that the power law distribution. A network follows a power law distribution when the frequency of nodes decreases according to a mathematical power. In simple terms, low degree nodes are extremely common. High degree nodes are very rare. For example, thousands of Facebook users may have 50 friends. Far fewer may have 500 friends. A tiny number have 5,000 friends. The exponent of the power law often written as B is typically between 2 and 3 in real world networks. So the power law PD equal to A into D power minus B. So D power minus B is the node degree. So some properties of power laws. So one challenge is that probabilities must add up to 1. To achieve this, mathematicians use a normalized constant. So based on the Riemann-Zeta function. The key practical idea is power laws are mathematically well-defined distributions and can be analyzed rigorously. This is the generalized zeta function. So then approximating A. So the exact calculations for power law distributions can be complicated. So instead we often use integration to estimate certain values. So this is the formula for A value. The next one is moments of power law degree distribution. So the first moment is a mean or average. The second moment relates to variability. So interestingly, it become extremely large or even infinite. So this is a unique property of power law networks and helps explain the presence of extremely highly connected nodes. So the more on moments. So in real life, networks are not indefinite. Every network has a finite number of nodes. For example, nobody can have more friends. Nobody, for example, every network has finite number of nodes. For example, nobody can have more than friends in a network of people. Therefore, real world network always have finite moments. However, the second moment can still be extremely large. This means hubs with huge numbers of connections will have a major influence on the network. So, power law degree distribution examples. In cell phone networks, the fraction of telephone numbers receiving k calls per day is approximately proportional to most number of numbers received few calls, while few receive many calls. And then book purchasing. The fraction of papers receiving k citations also follows. Approximately, most papers receive few citations, while a small set becomes highly influential. And the next one is social networks. Users with k incoming connections often follow. Most users have few followers, while a handful have millions. So the next one is power law distribution. So that the characteristics of power law distribution is small values are extremely common, large values are extremely rare. Examples, most YouTube channels have few subscribers. Few channels have millions of subscribers. So when we plot the data on a log-log graph, the curve becomes approximately a straight line. This straight line behavior is one of the strongest indications of the power law distribution. So the next one is elementary test for power law. So how do we check whether a network follows the power law? So choose a popularity measure, example number of friends, calculate the fraction of users with the degree. Next step, create a log-log plot, x-axis equal to log k, y-axis equal to log probability. Check whether the points form a straight line. If yes, the network may exhibit power law behavior. However, we have some important warning. A straight line alone does not prove a power law. Other distributions can sometimes appear similar. More rigorous statistical methods are needed, such as those proposed by Kalsit, Shalizzi and Newman. So the next one is power law distribution real networks. So scale free networks. So because there is no single typical degree scale. For example, some users have 10 friends, some have 100, some have 10,000. The pattern remains similar across scales. So the examples include Facebook, Twitter, World Wide Web and citation networks. So the next one is the long tail. One of the most important consequences of power law distributions is the long tail. A common assumption is most sales come from a few very popular products. But the long tail theory says a huge number of less popular products can collectively generate significant sales. Amazon example. So here approximately 50% of Amazon sales come from the long tail. This means best sellers are important, but thousands of niche books and products together contribute even more. So the key question is, do sales come mainly from a few highly popular items or from many less popular items? So the answer is often both matter, but the combined effect of the long tail can be enormous. So the overall summary of this session is power law distribution. Most nodes have few connections. A few nodes become highly connected hubs. This pattern appears in wealth, city populations, web traffic, citations, phone calls, and social networks. Networks following this behavior are called scale-free networks. The long tail effect explains why many low popularity items can collectively be very important. Thank you, students.